Assalamu alaikum, everyone. Welcome to today's class. So, in the last class, we were discussing the solution of DCOPF, and the approach that we adopted for the solution was the relaxation approach, which is in a way similar to the method that we already learned, named as the Karush-Kuhn-Tucker condition, application of Karush-Kuhn-Tucker condition for economic load dispatch problem. So, what we do basically here, it is basically a constraint optimization problem. So to start with, we assume that none of the constraints are considered. Okay, none of the constraints are taken into consideration to start with. And then we solve the ELD, conventional ELD in this case, because we mentioned in the last class that ELD is nothing but, sorry, the OPF is nothing but the combination of economic load dispatch and load flow. And more specifically, if we say it is a DCOPF, so the load flow will be taken from the DC load flow concept. So, and also in this case, we have some constraints like the line flow limits, constraints of the line flow limits only. And this line flow basically means these are the real power flow through the lines. So in the relaxation approach, what we do, to start with, we do not consider any of these constraints to be available. And we simply solve the DC load flow and the ELD. To start with, we solve the ELD. We look for the most economic dispatch to satisfy the demand. And then using those generation injection at different buses of the network, we try to find out the network line flows. And then we check back whether any of the line flow limits are violated or not. So in the example that we considered yesterday, we found such a case where among the 4 lines, line 1, 2, 3, and 4, line number 3 was found to be overloaded. So what we said at the ending part of the lecture, we said that in today's lecture, we will see how we are going to update the values of injection in these points. And we will do this keeping in mind that this flow has to be corrected, and this flow, which is beyond the maximum limit, this flow has to be taken equal to exactly to the maximum limit now. So instead of 66 megawatt, we have to make sure that the regeneration or redispatch of these generating units are made in such a manner that this value comes down to 60 instead of 66. And of course, at the same time, none of the other line flow limits are violated. Okay. Only then we can say, well, this is an acceptable or feasible solution for the DC OPF problem. So let us see today now how we are going to do it. So the concept that we will use for fine tuning or for resetting this line flow limits to its maximum limit, we'll be using the concept known as the generalized generation shift distribution factor. In short, it is GSDF, generation shift distribution factor, to be precise. So in here, let's define what is GSDF first. So GSDF means that if we have, let's say, let's draw the network. This is the bus. So we have 2 lines between bus 1 and 2. Then in each of those buses, we have generating units. Then we have a load here. And then we have the third bus. Also, we have a generating unit. Besides, we have a load demand. And also, we have another line between this bus 2 and bus 3. So what does generation shift distribution factor, or what information specifically will it give us? So it says that it will relate, GSDF will relate the change in power flow in line L. So any of the lines, we have 4 lines. So L can take any value starting from 1 up to 4. We have 4 lines. So the value of L will be taken from any of the lines. So change in flow in line L. So we are looking for any change in flow in the line. And this power flow will of course means this is the P line due to a change of generation at bus K. So the bus, for our case, the bus numbers can be taken from 1 up to 3. So in short, what we are looking for is that if, for example, our solution, the previous for the problem that we are considering currently, the ELD solution was this 230 megawatt output from generation 1, 20 megawatt output from generation 2, and 0 megawatt from generator 3. So while we obtained this ELD, then we found that this line was overloaded. So now we are trying to rectify the flow in this line, which is basically line number 3. We want to limit the line flow to 60 instead of 66. 66 was the result. We cannot allow this. Rather, we want to have 60, reduced flow. So for doing that, what we can do simply, we can reschedule the generation. And we have only 3 generating units to do this for this problem. So this relationship, this is known as the sensitivity we are looking for. So how much flow change will occur in this line when I change generation at this bus or at this bus or at this bus. So this will link injection at bus 1 with line flow at bus 3, or injection at bus 2 with line flow at in line 3, flow in real power flow in line 3, or injection from generation 3 or bus 3 with the line flow in along line 3. We are only bothered about line 3 because the line flow limit violation is occurring for this problem only in line 3. However, we have to generalize it in some manner. Okay, we have to generalize this concept in some manner. So that's why this concept will come, GSDF. It will relate the change in injection with the change in line flow. How much change in line flow we are going to expect for a change in injection at any of the buses, specifically the generation buses present in the system. So this is basically, this relationship is captured by GSDF, generation shift distribution factor. So in a sense, we can say that, well, I'm shifting some of the generation from this to other bus, or from this to other bus, or from this to this bus, something like this. Okay. So I'm trying to shift the generation from the current injection. Current generation is 230 here at generation point bus number 1. Here it is 20, here it is 0. I have to change, update the generations so that I can rectify the line flow limit violation. So for capturing this information, we will use a factor which is basically known as the generation shift distribution factor. Means while I am trying to shift the generation from one generator to another one, how will the line flow distribution be changed, or how will it affect the line flow limits? Okay, so in general, so that's why we are, because we are trying to generalize this relationship between the bus injections and the line flows. So that's why we are using to generalize index. One is L for the line number, K for the bus number. Okay, now to do this GSDF, to calculate this GSDF, there are 2 different cases. So let's start with case number 1. In case number 1, what we actually do, whatever generation is updated in the PV buses, is compensated, exactly compensated by the slack bus. Means what? Means the slack bus, basically the slack bus here, we are not going to update the generation at the slack bus. So to start with, okay, so the slack bus is basically our dependent variable. Independent variable is any other generation bus other than the slack bus. That's why I'm mentioning PV bus. Remember, slack bus, in the conventional load flow, we have three different kinds of buses: slack bus, PV bus, and load bus. Okay. Among load or PQ bus, among these three kinds of buses, load bus cannot inject any power. Okay, it can only take power. Okay, so as we are talking about injection of generation, so load buses will not come into consideration for this topic of GSDF. So only two options are available. Either we can change the injection from the slack bus, or we can change the injection from the PV bus. So in case one, what we say, that we change the injection, whatever amount of change we are making in one of the PV buses. So for this example, it could be either bus number 2 or could be bus number 3. So what is meant by this line is, whatever change I am making at bus number 2 or bus number 3, that change will be captured or compensated by this slack bus. So it means what? Means if I go for numeric values, then it means, let's say, for rectifying this value of 66 to 60, for bringing down this value, line flow limit for the line number 3 from 66 to 60 megawatts, let's say what one option could be, let's say after we apply the algorithm that is we are going to discuss next, let's say the algorithm finds that we have to change this generation at bus 2, I have to reduce it to 10 megawatt. Okay, I have to reduce it to 10 megawatt. It means what? It means if I am reducing this generation by 10 megawatt, then who is going to compensate this loss of generation or reduction of generation? This line says in case 1 that all these loss, in this case it is loss reduction, all this reduction of generation at bus number 2 will be or should be compensated by this. That means if at bus 2 this is a reduction in generation, in the slack bus, in bus 1 for our case, that same 10 megawatt will be supplied by the slack generator alone. What is the necessity of supplying this? Because remember, we are not reducing any load. So the load demand is still 250 megawatt in total. Total load demand is still 250 megawatts. So I have to satisfy this 250 megawatt in any way. Okay, in any way. So that is one of my equality constraint. So when I say let's say, for example, I am planning, or my solution says we have to reduce 10 megawatt or change 10 megawatt at bus 2. It could be reduction or increase. So let's say, for example, now we say it is reduction. So that reduction in 10 megawatt will be supplied by the slack bus alone. So it will become 10 at bus number 2, whereas it will become plus 10, minus 10 at bus number 2. So it will become 10 and it will become 240. Let's say there is no change for the time being. So 0 remains as 0. So that in total, you still have 240 plus 10, 250 megawatt demand is satisfied. This is case 1. Okay. So if that is the case, then this alpha LK for case number 1, in general, alpha LK can be represented by this, where alpha LK, alpha is itself the GSDF of line L. So the L index will come first, appearing first in the subscript, the line which we are taking under consideration. For our case, it is line number 3. We are trying to update the flow of line number 3, update or change the flow of line number 3, or check the flow of line number 3. So GSDF of line L. So L will come first, and then K. K is the injection of generation, the bus number where we are injecting updating our generation. So as mentioned here, so the first subscript for the GSDF is taken for the line number, and the second subscript for the GSDF is taken from the bus number. And then it relates the change in line flow or branch flow. So del PB, del P means change in real power flow. B stands for the branch, any branch or branch flow. L is the line number under consideration. Similarly, del pk in the denominator over here, del p again change in real power. K is the bus number where we are considering the injection change, and then to make it clearer, we are also writing it ing, in short means injection. So alpha Lk is simply the ratio between change of line flow at line number L due to the change of injection of generation at bus number K. So this is the definition of GSDF in general. And these are the explanation I have already mentioned. So now that we have the definition of alpha Lk, to find out what it actually is, we have to know what is basically our del PBL and what is basically our del PK injection. Once we know these two expressions, then we can simply say, well, if I know what is meant by del PBL, is there any equivalent expression? What is meant by del PK inject? Is there an equivalent expression? Or is there any expression which relates the ratio, which relates these two by a certain ratio? Then we can say that ratio will be simply alpha Lk. So let us see now how we are going to derive the expression of alpha Lk in terms of network parameters alone. Okay. So you can see now we are again taking help of the DC load flow, and specifically we are talking about the power injection relationship. Remember, the power injection means the injection at a certain bus. Injection means, again, this is the summing junction, this is the PG, this is the P demand, and this is the P injection at a certain bus. So this is plus and this is minus, and this is the bus. So this is the P injection. And if you remember, in the DC load flow, when we discussed about the injection power, real power injection at a certain bus, and when we related this with the corresponding theta angle, bus voltage angle, then we used a reduced dimension vector or array for P injection, a reduced dimension B prime matrix, and a reduced dimension for theta. Why? Because we said that this theta at the top belongs to the slack bus angle, and the slack bus angle is already known, it is 0, so we didn't consider it in our solution process or solution steps. So that's why it was a reduced dimensional relationship. Now from here, what we did, we made the theta as our unknown. Still the dimension is n bus minus 1 by 1 equals, this has to be inverted, so we have to invert B dash matrix, so it will become B dash inverse. Again, the dimension remains same, n bus minus 1 by n bus minus 1 multiplied by the P injection matrix, n bus minus 1 by 1. And now the inverted B dash matrix, the inversion of B dash matrix, because remember, B dash is nothing but the susceptance, imaginary part of my admittance matrix. If I take the inverse of that, I should expect some form of reactance. Okay, so that's why we are naming it by capital X prime, and the dimension will remain as it is even after the inversion, and we have P injection n bus minus 1. And then we have, okay, this is, I think, okay, this is, I think, the repetition of the same line. So it is the same as this. Oh, no, sorry. So here we have what now? These were the actual theta variable. This was the X prime or X bar matrix originating from the inversion of the B prime matrix. And this was the actual P injection, the actual value. Now, in the next line, what we do, we take the incremental form. Okay. So we say, what would be the change in theta due to some change in injection? Okay. So now we are not interested in the actual value, rather we are actually interested on the change in that variable. So you see del theta now, dimension is still n bus minus 1 by 1. X, there is no del X prime, because X or del X or X prime, B prime, these are functions of network parameters, line parameters specifically. So, and it is assumed that the line parameters will remain constant. So there is no del x dash. Del x dash is simply a constant matrix. So it will remain as it is as a constant matrix. However, there will be change in the injection. So this is the actual relationship or relationship between theta p and x dash in actual values. However, this one is in the incremental values, in terms of the incremental values. So once we have it, then what we will do a little update on the notations. You see specifically the notation of x prime, and that will also update the dimensions here. We'll also update the dimensions here. So what does it mean? It means that now instead of x dash, what we are doing, we are simply taking the full x, okay, the full dimension of my network. By network, we mean how many buses are there. Okay, if there is n bus, n bus, so the dimension of x will be n bus by n bus. Up to this point of our derivation, it was n bus minus 1 everywhere, n bus minus 1, n bus minus 1, n bus minus 1. Considering the del theta, remember the topmost theta was not taken into consideration. The topmost theta, theta 1, was not taken into consideration over here. So similarly, up to this point, that topmost entry del theta 1 was not included here. However, it has been included here. So now, if it is a 3 bus system, so this array will look like this: del theta 1, del theta 2, and del theta 3. So this is how it will look like now, the full dimensional array. And what about x? We will discuss it here. I'm coming to that point. Let me finish the del p. So now this del p will also have the full dimension: del p1, del p2, and del p3. Okay. Whereas here it would be only del theta 2 and del theta 3 without including the del theta 1. And here also it is only here also it is del p2 and del p3. So we are basically updating the x matrix, and to keep the dimension of all these vector and this matrix and this vector compatible with each other, we have to update this left hand side entries and also this entry. Okay, so what or how we are actually going to calculate this x matrix? Let's see how we are going to achieve this x matrix from this x dash, and what is the reason behind that. For a 3 bus system, remember the dimension of x dash should be n bus minus 1 into n bus minus 1, and the entries will be like this. This is nothing but b prime inverse. Remember, b prime inverse. So simply in the b prime, if we write down b prime like this, b11, okay, it was not b11, it was b22, because it was reduced dimension, b23, b32, b33. Okay, so this was the dimension, this was the entries of the b dash. Once we invert this, we will call this inverted of b dash. So b dash inverse would be simply x dash, and x dash we are simply calling it x11 dash. So all the entries we are simply putting dash. However, this is arbitrary. I mean, you can also take it like x22 dash, just to keep the symmetry with this b dash matrix. You can also call it x22 dash, x23 dash, on x32 dash, and x33 dash. I'm just simply naming it like this. Doesn't matter. You can change, update this subscript also, just to keep it symmetric notation. So this is the reduced dimension. And then from here, we are going to update the dimension simply by adding an additional row and additional column as the first row and the first column of the updated matrix with all 0 entries. So simply it will be all zeros here, and here I have my original x dash. So this is how we are going to get it. So the question comes, why all these are zeros? Why are all these zeros? Okay, the reason is remember the slack bus angle. The slack bus angle theta 1 is our reference. This is our reference for the solution of the load flow analysis. Be it DC load flow or the AC load flow, doesn't matter. So as because this is the reference angle, we will not allow the slack bus angle to deviate from 0. In other words, theta 1 or the change in theta 1 should be maintained at 0 so that the actual theta 1 is kept as its original reference point, original reference value. Okay, so this is the reason why all these entries are 0. It means what? It means even if we inject additional power, or if we reduce the injection of power from any of the buses, it should not affect the value of del theta 1. However, it should affect the other remaining angles of my network. So this is why all these entries, added entries, are kept as 0 to make sure that del theta 1 is 0, which ultimately means my theta 1, the reference angle, is remaining at its original value of 0. So we are not allowing theta to be deviated from its reference value simply by putting zeros here in the first column and in the first row. Okay, so now that we have the del theta, okay, which will give us the change in theta value, of course, that's good. So what we are going to do now, we are going to see how we are going to get some specific theta expression out of this generalized expression in the next slide. So let's say now that some injection del P inject, this amount of power is injected at bus K. Okay, remember we are still following case 1. So del P injection amount of power is injected at bus K. It could be the reverse case also. Remember, we may also say that this, okay, what it means, del P injection, I should say del P injection could be positive, could be negative. That means the injection could be increment in the incremental form or in the decremental form, in both ways. Okay, so once we have a del P injection at any bus K in my system, the same injection or same amount of power will be lessened from the reference bus alone. So that means del P injection here, we are considering it to be positive change. So the slack bus or the reference bus should take care of that change. So only the slack bus will be responsible for compensating this change of injection at any other bus K in the system other than the slack bus. So if that is the case, then we can write down a big array like this for n bus in general. So let's say del theta 1 up to del theta I, then del theta j are any two intermediate buses. Then we come down to del theta k, where the injection is taking place. So it is an important bus. Then up to the ending bus is n bus. Okay, del theta n bus, n number of buses. Then of course I will have x11 up to xn bus. Similarly, x11 up to xn bus 1. And like this, we can fill up this big X matrix. Keeping in mind that these entries, remember, these entries belong to del theta 1. Also, these entries are connected to del theta 1. So these are nothing but zeros. These are nothing but all zeros. Okay. And here dot means we have some more entries, but these are not typed over here, shown over here. Okay. So now about the, so this is my del theta, which is equal to del theta array is equals to x into del P injection. And we are considering the del P injection is happening at bus number K. So you see del P injection at bus K. So this is the entry of bus K here. Okay. So this is the column, this is the row number for kth bus. So at the kth bus entry, we will have some injection, and that amount of injection, if it is a positive injection, which we have considered here, the same amount of injection will be lessened from the reference bus. So means it is a -1 for the reference bus entry, the first column of the P injection array. And so in this exchange of power, in this scenario, under this scenario, no other buses are taking any injection. in terms of reduction or increment. Okay, so there is no decrement or increment of injection at any other buses of the network. So the only two players are there. The first player, the compensating player, is the reference bus, or the initiating player is the kth bus. Okay, so if this is the case, then for any two buses other than the kth bus, any two buses other than the kth bus, and of course the slack bus, any two general bus, theta I and theta j, how can we relate this change of theta with the change of P in terms of the X matrix entries? Let's see. So what would be del theta I? Del theta I would be what? Del theta I, we can say only two. So only two entries are there. So I can write del theta I equals to, it would be this row multiplied by this column. Okay, so you see only two non-zero entries are there. The first non-zero entry is this, so it is -1 into x11. And another non-zero entry is this, it is plus xik, this is xik into 1. Okay, now what is the value of, okay, so this and whole multiplied by del P injection, remember, so the whole multiplied by del P injection. Now what is the value of x11? Remember, this whole row and this whole column are 0, so simply this will be 0, and we will be only left with xik into del P injection. Okay, so this is what is del theta I simply in terms of network parameters and P injection value. So in the same logic, using the same logic, we can write for any other buses del theta j is xjk del P injected. Okay, so this is how these two equations are obtained over here. So once we have this change in theta values obtained in terms of network parameters and power injection at kth bus, we have obtained some useful information. We will use it later on. So remember, del theta I is xik into del P injected k. Okay, we'll use it. So we'll keep this as it is because we will need it later on. So now, talking about the power flow, because remember, our target is to find out alpha Lk, which is equal to del P of the branch number L divided by del P K injection. Okay, so this is basically, should write del P injection K. Okay, so we have got some relationship of del P injection, okay, del P injection at K in terms of the change in angle and the network parameter. So it means we can also write del P injection K if we want. Del P injection K is nothing but del theta j by xjk. Okay, del theta j by xjk. We can also write del P injection K is del theta I by xik, and so on. So some sort of relationship has already been obtained. So now we want to focus on the numerator of this GSDF expression. So let us see. Again, we resort to the DC power flow, and now we are focusing on the line flow. Okay, real line flow or real power flow in line L, and considering this line L is connected between two buses, arbitrary buses I and J. Okay, means this is my line number L. This is connected between two buses I and J. So what is the line flow? Already derived in the DC power flow lecture. So this is PBL, and PBL is nothing but theta I minus theta j, considering L for the Lth line, the sending end bus is I and the receiving end bus is J. So it will be theta I from the sending end bus voltage angle minus receiving end bus voltage angle divided by the line reactance, divided by the small x. Remember, this is small x. So this is the line reactance for the Lth line, which is present between bus I and bus J. From here, we can write the incremental form again. So del PL again equals to del theta I minus del theta j, and xij will be as it is unchanged because it is a network parameter considered to be constant. So there will be no change over here. Now del PL equals to what? So you see, we need now del theta I as well as del theta j. So bring those from this expression del theta I. What is del theta I? Xik del P injected K. So Xik del P injected K minus del theta j. What is del theta j? Xjk into del P injected K. So Xjk into del P injected K divided by Xij as it is. So now you see we can simply relate del PBL divided by del P injected K. That means this one is nothing but simply this part Xik minus Xjk by Xij. So, and this ratio is nothing but our required GSDF. So in a sense, we say that we have derived the expression of alpha LK in terms of network parameters. In terms of network parameters, Xij is nothing but the line reactance of the Lth line. Xik, Xjk, these are nothing but the entries of the big X matrix, which is obtained from the B dash matrix. B dash matrix was obtained from the Y bus matrix. So Y bus matrix was obtained from the line data. You see the information flow. So this is how we actually can get Xik and Xjk very easily. So Xik, Xjk are functions of line data. Xij, small xij is also function of line data. So means these all are now, the alpha Lk is now represented in terms of the network parameters of the line data alone, which are unchanged. As long as the network is unchanged, intact, these alpha Lk will remain constants. And this is what is mentioned over here in this box. As long as the network remains unaltered, your alpha Lk are constants. You don't have to recalculate it every time. So now that we have obtained the alpha Lk values or expressions of alpha Lk rather, we can use these expressions to find out the new line flow. The new line flow. What does it mean? So it means we are targeting this. We have we are trying to find out basically PBL new. I should write. Let us write it over here. If I try to find out after generation dispatch, okay, remember we were talking about generation dispatch. With the generation dispatch, our target was to find out some updated line flow. So if I'm looking for some updated line flow, that would be PBL, P branch flow for line number L, and that is the updated one. It should be, of course, related to P branch flow for the same line, the old value plus the change happening due to the rescheduling of the generators. Okay, del PBL. Okay. So this one, how can we write? PBL old plus what is del PBL? You see, from here we can find out del PBL is nothing but, now we can write alpha LK into del PK injection. So this is simply alpha LK into del PK injection. So you see, by knowing this alpha LK, we can, if we know how much power is injected here, we can calculate del PBL. That will help us to update the old line flow and thus reach to the value of new line flow. So this is the essence or the necessity of GSDF, or the application of GSDF. We may say also in that way, application of GSDF in updating the line flow in using the DC power flow calculation in the DC OPF problem. Okay, so this is how we are going to do it. Now remember, all these were done considering that there were only two players. Okay, only two players. The players were the kth bus, where the injection was initiated, and the compensator, which was the slack bus. This was the compensator. So these were the only two players while we derived this expression. Now, if we say, well, besides the slack bus, okay, the initiator will remain the same, okay, in the next case. However, instead of providing the compensation from only the slack bus, we want to take, or we want to have participation from all the remaining PV buses. Of course, other than the kth bus. Okay, kth bus is the initiator. So the compensator should be all the remaining generator buses, means the slack bus as well as the PV buses. So if that is the case, then simply we will resort to the superposition principle. Specifically this one we will see in our example problem. Okay, so this is basically, we can say, case number 2 if you want, that instead of only the slack bus, the compensating buses will be, or the compensating generators will be all the remaining generator bus other than the initiator bus or the kth bus, where the injection originally started, change in injection originally started. So with all this information, now we are ready to apply our knowledge of GSDF to our DCOPF, the problem that we started, but we couldn't finish because of the lack of knowledge. But now we have the knowledge of GSDF. We know how GSDF can be utilized to find out the updated line flow. So now we will go back to the same problem. Okay, and let's go back to this slide first, and we will try, using the knowledge of GSDF, we will try to limit this flow or update this flow and try to fix it at 60 megawatt maximum. And in doing that, we will see how we are going to update the contribution of the generating units. Okay, so this is the next part of the solution of the same problem. Okay, so now we continue again the relaxation approach. So we used the complete relaxation, means we didn't consider any of the line flow constraints, but that didn't give us any feasible solution. So we will resort to now a less relaxed solution. Okay, less relaxed solution. So we will impose a new constraint. We will impose a new constraint, meaning that branch power flow for line number 3. Remember PBL, this is PBL. Branch flow at line number 3 cannot exceed 60 megawatt. So this additional constraint will be added in our formulation of DCOPF. Okay. For doing this, what we will do, we will use the knowledge of GSDF. And here we will consider that all the generating units are participating, not only the slack bus, all the generating units are participating in our redispatching solution. Okay, so how we are writing it? Simply, we are writing it like PB3 new. 3 is the PBL, L, line number L. PB3 new is equals to PB3 old plus, now we say there are multiple injections, multiple generator injection, multiple compensating generators. Okay, so this change or this update will occur when all the generating units are participating. So we have 3 generating units. So generating unit number 1 is injecting some power, generating unit 2 is injecting some power, generating unit 3 is injecting some power, and this injection is related with the line flow by the GSDF. So you see alpha 31. So what is alpha 31? Alpha 31 means this is the GSDF relating. Remember, the first entry is L, second entry is K. Alpha LK, alpha LK. By definition, alpha LK is this: del PBL divided by del P injection K. Okay, this is the general definition. So alpha 31 means what? Means I'm looking for the change in line number L. In our case, it is 3 for the injection change in line number, generation number 1 or bus number 1 2, 3, and whatever number is there. So here multiple generating units are participating in the redispatching or in the correction process of the line flow for line number 3. So alpha 3, 1, it will relate line number 3 over here and generation K, that is 1. So 3, 1, 3 for L, K for 1. Then alpha 3, 2, 3. So line remaining same. Okay, line remaining same because only line number 3 is into our consideration. This is the line where the limit violation has happened. Line number 3. This is our L. L will remain same. K will change. Alpha LK. So alpha 3, 2. So 2 means this is the injection for bus number 2. So del P injection 2. Alpha 3, 3. Here K is equals to L. So L is still 3. K is the injection at bus number 3. So this is how all the generating units are participating for correcting the line flow of line number 3. So if this is understood, then PB3 new, this is what we want. Okay, so this is what we want. We want how much power to be flowing? We want 60. We want 60. So this is 60. PB3 old, how much is it? It is 66. This is the original result or actual result obtained after applying ELD. So this was carrying 66 and that was creating problem. This is the issue. This is where everything started. All the problems started. Then alpha 3, 1. What is alpha 3, 1? Alpha 3, 1 is can be taken from this matrix. This is our alpha matrix. So what is alpha 3, 1? Alpha 3, 1 means what? So this is our L and this is our K, and I have to take xik minus xjk entries divided by xij. So I have to know what are the index of I and j for this line number 3. So in the line number 3, we go back. What is the sending end bus? I and j means it is the sending end bus and the receiving end bus respectively. So the sending end bus for this is line number 3. Sending end bus is 1, receiving end bus is 3. So 1 and 3. So I is 1 and j is 3. So here I is 1. We have I equals to 1, j equals to 3 for alpha 3, 1. Okay, for line number L. So it is common for all alphas. For all alphas, L is fixed. Remember, L is fixed. So I will remain 1, j will remain 3. K will update. K will be updated for all these entries. So this is xik. So I k is 1, I is 1. So x11 minus x jk, xik minus x. Let me write it. Alpha lk is xik minus xjk. All these two x, both of these x are capital and divided by small xij. Small xij is the line parameter. So xik, I is 1, k is 1, I1 x11 minus xj, j is 3 and k is 1. So x31 divided by x13. You take the values from the x matrix and the small x data entries. So what are the x11 and x31? Let us see. So x11 will now become this one, x11, and x31 is this one. Okay, so both of them are 0. Both of them are 0. So I'm not taking the value of xij because it doesn't matter. So 0 minus 0 divided by small x13 is 0. So alpha 31 is 0. And in this manner, we can calculate all the remaining entries of this alpha matrix. Okay, this is the process. You identify what is your I, you identify what is your j, you write down the formula for alpha lk, you identify what is your L, you identify what is your K, and then you simply add, you simply calculate this. I have shown this one, alpha 31. So this is your alpha 31, which is 0. So alpha 31 is 0, so it doesn't matter how much del P injection is there, it will not, this is the generalized expression. So I'm writing alpha 31, okay, it will come in the next line, of course. So del P injection means what? Change in injection at bus number 1. So This is the new value of generation. This is the old value of generation. So old value minus new value is the change in injection. Sorry, new value minus old value. Sorry, new value minus old value is the del P injection at bus 1. Similarly, new value at new generation at bus 2, new generation at bus 2 minus old generation at bus 2 multiplied by alpha 32 plus alpha 33 new generation at bus 3 minus old generation at bus 3. Okay. So now what do we know and what are the unknowns? Let us see in the next line. So alpha 31, we said it is 0. So you don't see G1, any G1 in this line because alpha 31 is 0. So we come to alpha 32. From this table, alpha 32, remember I have shown only the calculation process of alpha 31. I hope you can complete the remaining entries for this table. The same process, following the same process. So alpha 32, what is alpha 32? Alpha 32, alpha 3, third column 32. So this is alpha 32 minus 0.2 G2 new, which we don't know, G2 not, which we already know. Remember, this is the generation of generating megawatt of generating unit number 2, which was 20. So the generation was like this: 230, 20, and 0 for PG1, PG2, and PG3. PG1 is not appearing here because alpha 31 is 0. Okay, G1 0 is not appearing in this line because alpha 31 is 0. Alpha 33, alpha 33 minus 0.6. G3 new, we don't know. G3 old is 0. Okay, so now we simplify it. So after simplifying this, we get 70 minus 0.2 G2 minus 0.6 G3. And in here, this PB3 new would be 60. Okay, this would be 60. So our new constraint would be 70 minus 0.2 G2 minus 0.6 G3. This value should be such that it is less than or at best 60. 60 is the PB3 new, the new value that we can allow, the maximum value that we can allow. So this is the new constraint, and this new constraint has to be added to our previous formulation of DCOPF. Okay, so this is a stricter version or a tighter version of DCOPF compared to our first trial. In the first trial, this constraint was not there. However, without this constraint, we failed to find out some feasible solution. That's why we adopted the concept of GSDF, and using the concept of GSDF, we have found a new constraint, and now we will append it, we'll add it with our previous formulation of DCOPF. Let us see how we are going to do this. So this is how. So this is our original cost function. It will remain as it is. This is the new or updated constraint, colored or highlighted in red color. How we are getting it? Our equation is 70 minus, okay, let's see. So you simplify this. So this is minus 0.2 G2 minus 0.6 G3 less than equal to 60, and this will go to the other side. So this will become 60 minus 70. That means this is simply minus 10. And then we change the signs and also remove the decimals. So what we will get, first we remove the decimals. So it will become 2G2 minus 6G3 should be less than equal to minus 100. And then we remove the negative signs. So we will get, we are changing the signs. So we have to also change the direction of this inequality. So it will become greater than or equals to 100. So this is how we are going to get this new constraint from this equation, from this inequality. So this is what is written: 262 plus 6G3 greater than equals to 100. And remember all the previous constraints, by that I mean the equality constraint over here, and all the generation limit constraints are still valid. This is a new line flow limit constraint, line flow limit constraints, because of the violation of the previous attempted solution. Okay, so now that we have this, remember this is again some straight line. This is a straight line. So this straight line we can take the coefficients of this G2 and G3 as 1, so that we can have something like x1 plus x2 is something greater than like this. So for doing that, what we can get, we can say, and some intercept basically, x1 over a plus x2 over b greater than equals to, let's say, 1. So the straight line inequality. So we are now looking for the intercept in the x1 axis and intercept in the x2 axis, keeping this equals to 1. So what we will get, simply we will get G2 over 50 plus G3 over 100 divided by 6. It will come as 16 point something, something like 6 fraction, okay, greater than equals to 1. So we have got a straight line equation with the intercept for two of the variables, two variable inequality. And now this new inequality or new constraint would be imposed on our graph. Okay, so G2 over 50 plus G3 over 16.66 means we have a straight line where the G2 axis will have intercept equals to 50 and G3 will have an intercept equals to 16.66 something. So you see, we have a new constraint added where G2, this is the G2 axis, remember, G2 intercepted at 50 and G3, this is the G3 axis, intercepted at 16.6667. And then we simply, so these are the 2 points, terminating points of the line, and simply we join the line, okay? So now what is the feasible solution space? Okay, and this line is introduced due to the pre-fault flow limit violation on line number 3. Pre-fault flow limit violation on line number 3. Okay, so now what we do, we again analyze the feasible space. What is the feasible space? Okay, so this is no more the feasible space. Previously, this was only infeasible, okay, within the graph, and also these were infeasible, these were infeasible, these were infeasible. Now this part, this small triangle, this is also infeasible, okay, because why? Because this says this should be greater than G2 over 50 plus G3 over 16.67 should be greater than equals to 100. Sorry, yeah, greater than equal to 1. Okay, greater than equal to 1. So greater than means we have to look into this zone. We have to look into this zone of solution. So that means we have to look into this zone of solution. Okay, we cannot go smaller than that. Okay, any value here will not satisfy this inequality, any value over here. So this is no more a feasible solution space. Or only feasible solution space is, if I draw the boundaries now, the only feasible solution space is now a tighter one, okay, a tighter one, tighter version of the previous form. So the only feasible solution space is this. Let me draw it by some new color. Okay, so the only feasible solution is feasible solution space is this. So this zone is now our feasible solution space. So you are missing out here. We are missing out in this zone. This is no more feasible due to the introduction of this constraint. So this is what is mentioned. We have still in the G2, G3 plane, we have still the upper limit and lower limits represented by the blue and red colors. The flow limit on line 3 cutting off the previous solution. This is what is meant by this. We are adding this constraint, and because of that, some part of previously feasible solution space is no more feasible now. Now the question comes, which generator should we use to relieve this overload? By overload, I mean line overload. Okay, so should I go for increasing G1, or should I go for increasing G2? Should I go for decreasing G2? I mean, what would be our approach? Okay. Okay, so now if our solution here can be Remember, in the linear programming approach, this is the graphical approach of linear programming. The solution points could be only the corner points. The corner points. So these are the possible solutions. Okay. And in each of these solution points, we can check the cost. Okay, this is one way. However, if we remember that our previous solution was lying here. Okay, our previous solution was lying here. So intuitively, we can assume that our solution could go at this point or at this point, the minimum solution. Okay, this is the graphical way. Now we have to also satisfy it with the help of calculation. Okay, whether our choice is a valid one or not. So let us see. Keeping G1, remember we also said that because this is an ELD, inherently there is an ELD problem. So we have to make sure that all the generators are participating. And if we want to make sure that we cannot take any value for G1 more than 230 because what? Because why? Because you see our demand is 250. Minimum G3 can support is 0, it's fine. But the minimum G2 can support is 20. So that means the maximum we can take from G1 for satisfying this 250 is only 230. Okay. So G1 here is playing no further part. Remember, G1 here is playing no further part. So the only two players for redispatching would be G2 and G3 because of the given values, So the generator, I have two choices only. I can go for G2 or I can go for G3. If I am going for G2, generator providing relief is G2. In that case, G2 will take how much? Okay, if I'm taking, that means I have to take this solution. Okay, so means I am shifting from this point. What is means generator providing relief? What it means, I was taking this much from 230, taking 20 from G2 and 0 from G3. This was the point. Now I'm shifting to either this point or this point and checking the cost, associated cost. So G2 providing relief means what? Means G3 is still not participating, but G2 will increase its generation. G2 will increase its generation. So it means I have to go along this line. And this is the point which is a feasible solution. So G2 will give me how much? G2 will give me now 50. I have to take 50 from G2. From G3, I will still take 0. So because the demand is 250, from G1, I can only take 200. So this is the new ELD at this point. What is the cost? What is the cost? What is the cost of G2? Let us go back to the cost values. It's the cost. Okay, probably, yeah, 20, 40, and 50. 20, 40, and 50. So 20, 40, and 50. So means what? What we are going to get, 20, 40, and 50, we were here. Yeah, 20, 40, and 50. So what is the cost? 20, 40, and 50. So 20 into 200, 40 into 50 plus 0 for G3. So it is 4,000 plus 2,000. So it is 6,000. Our previous cost was how much? So that means if I'm taking 50 megawatt from G2, G3 is still 0, G1 is 200, then my cost of energy production, power production is 6,000, whereas my previous solution was only, 5400. Yeah. What is that? Yeah. So the previous solution in slide number 15, it was 5400 with this combination 230, 20, and 0. I have updated the combination. one of my probable solution, G250, G30, G1 200. So it is 6,000, means the gap is 600. So the cost is increased by an amount of 600. So that is 6,000, the new cost minus the previous cost. So that is your 600. So this is the 600. Okay. And what is generator provide? Now, if instead of that, if we look for this solution, means instead of going in this direction, if I go in this direction, I will find this point, one of the feasible solution. What is the combination here? What is the combination here? So the combination here is your G, okay, how much is it? Yeah, here it is. G2 is 20. So this is the G2 line, 20, still 20. So G3 is 10. G3 is 10. This is one way to take it from the graph, but however, you can also solve for the value over here for G3. Okay, this is the equation for G2. G2 equals to 20, and this line are getting intersected. So what is the equation of this line? This line equation is nothing but how much is this? Let's check. 2G2 plus 6G3. Yeah. So this line means it is 2G2 plus 6G3 equals to 100. So we are looking for the intersection and we are looking for the value of G3 here. So we put 20 over here. So 40 plus 6G3 equal to 100. And if you solve this, you will get G3 equals to 10. So you take G3 10, take G2 20, this point. So it gives you gives you 30, 20 plus 10. So 250 minus 20 minus 10. So this is the demand. This is your G2. This is your G3. So this will be your G1, which will be equal to 220. So now you are getting 220 from G1. So now your solution ELD is 220 for G1, 20 for G2, 10 for G3. What is the cost? The cost can be calculated for this combination. Let's calculate the cost. So the cost was, again, what was the cost? What was the cost? Yeah, the cost was 20, 40, and 50. Sorry, I'm forgetting it every time. 20, 40, and 50. So let me write down the cost here. 20, 40, and 50. So 20 into 220 plus 40 into 20 plus 10 into 50. So how much it is? It is 4400 plus 800 plus 500. So it is 4400 plus 1300. So it is 5700 total. Our previous cost was 5400. So the new added cost would be 5700 minus 5400 equals to 300, which is written over here. So which one is less costlier option? This one is the less costlier option. So we will go for it. So our new ELD solution will be this point and not this point. Okay. So this shifting will give us less cost, will yield less cost for the operator. So that would be the solution. That would be the solution. And this is what we are summarizing here. So we are saying that our new optimal dispatch would be, because we are going for the cheaper option, which is generator 3 providing some relief. So the optimal dispatch is now G1 equals to 220, G2 equals to 20, G3 equals to 10, and the associated cost is 5700. The additional cost is 300. So now with this, we have made sure that line 3 limit is not violated. Okay, but what about the other lines? We have to also check that. We cannot leave those alone. Okay, we have to also, with this solution, 220, 20, and 10. So 220 PG1, 20 PG2, 10 PG3. We have to again recalculate the line flows. Okay, so what would be the line flows? What would be the line flows? We know what is the line flow, PBL. So you will apply the PBL formula. So PBL, L is 1 and 2. So it would be simply, yeah. So PBL, we know how to solve it. So let us see how did we do that earlier. So PBL is, yeah, that big formula actually. So PBL is basically, okay, where is that? So PBL, the PB matrix, okay, the line flow array is simply the base MVA multiplied by this B small b line matrix multiplied by the A matrix, the node incidence matrix multiplied by the P injection. So this is the PB, okay? So PB means P branch flow. We apply this. Now we have this updated only. B line is taken from the line parameters. A is the node incidence matrix as long as the line connections are all intact to the base case or the initial case. A will remain constant. 100 is coming because of the MVA base. So only the P injection is updated. Now we have 220, 20, and 10. Previously we had 230, 20, and 0. So instead of this, we are having this. So once we apply this formula, we get all the values and we check back with the limits to the given problem. And we find that all the limits are now unviolated. Okay, all the limits are within their permissible values. So this is a valid DCOPF solution. This is the conclusion, the valid DCOPF solution. And we can also check back the balance between load and demand at each bus. This is the last thing that we can do if we want. For example, if we say, what is the load generation balance at this bus? Okay, the load is 200, generation is 20. Okay, so 80 coming in, 80 coming in, so 160 coming in, 20 also coming in. So 180 is coming in, going into the bus from this side, from the line. 180. 200 is required. Okay, 180 is taken from the other generators through the lines by this bus. 200 is required, so another 20 is required, so that is supplied by the local generator. So this is the balance. Similarly here, 60 coming in, okay, 20 going out, so that is 40, and the demand is 50, so another 10 is required, so this is the remaining 10. And remaining balance should be checked also here. 220, there is no demand, so simply you have to add up this line flow, this line flow, and this line flow, and you should get back to 220. So you are getting it. 80 is 80 plus 80 plus 60 is basically your 220. So this is the one example, I should say, of DCOPF application where we have seen that we can go for the relaxation approach, a fully relaxed approach to begin with, and then we have to check back with the line flow limit violations. And we have also shown that what we can do if there is any line flow limit violations. With the help of the GSDF, we can rectify the line flow limit violations. And then, of course, we have to keep continuing the checking. Okay, we have to keep the checking of the line flow limit violations in a continuous manner. However, in this case, for this example, with one redispatching, one step of redispatching of the generating units, we have corrected all the limit line flow limit violations. So that is our DCOPF. Means this is the least costliest option of generation, satisfying all the line flow limit violations and satisfying the load generation balance. Okay, so that's all for DCOPF. I will post it in the classroom, inshallah, the recording. And from the next class, we will go for a new topic, inshallah. So see you soon, inshallah, in the classroom, in the physical classroom.